Hello and welcome back. Good to see you again to the second part. And the second part will be about spectrally third correction methods, the multi-level extension of that, and then the parallel in time scheme applied to the Scheller-Ward equations, so related to the weather simulations. And that's a joint work together with François Hamon and Michael Minion. So Michael is one of the developers of that FAST algorithm and I think also ML-SDC. And that's how the, what I'd then like to talk about, so the FAST method, that's how it suits, or how that fits to these different research directions. So let me break that down into different parts, and that's also how the FAST method has been developed at the beginning. So first, the spectrally third correction method, then the multi-level extension version of that, and then last but not least, the parallel in time extension of that. The underlying idea of spectrally third or defect corrections is that if we have a Cauchy problem given of the following form, that our time derivatives are given by that function evaluation, then we can, and given of course that initial condition, then if we have, or if we know a way to provide a first order accurate time integrator, like that stability function R here, to evaluate time step or time integration for that particular time step here. If we have that, and if we can provide that, whatever method that is, maybe whether it's explicit, implicit, or exponential, then it is possible to just take that SDC method from a pure black box point of view in order to develop a higher order time integration method. So the user of that method only needs to provide that lower order, typically first order time integration method, and then we get a higher order time integration method basically for free, at least regarding the implementation aspects. So on the following slides, I'm just providing some sketches about that to make it a little bit more intuitive for you what that means. And what you see here is one time step. So that's basically delta t, which we see here. That's just one time step. And you also see these time step sizes here. And these are based on Gaussian quadrature nodes, since otherwise we would run into the Runge effect. What you see here is a reference solution given by these guys here. That's just an oscillatory ODE system with the real and imaginary parts. And after the first iteration, so the very first SDC iteration, we only get a first order accurate approximation of that. That's not even here anymore on the plot, but that one here would then be a first order accurate approximation of that reference solution. And now, by having these deferred corrections, we can apply another iteration, where we see that after the first correction we end up with that solution. After the next one we end up with this one here, and then step by step, if we do more correction iterations, we see how it more and more closely resembles the real solution, how it should be here in the end. So if we now do 7 iterations here, 8 iterations, and now 9 iterations here, it already closely matches the results. It's quite impressive what this method can do. So just by providing a first order accurate time integration method, you can just get down to whatever accuracy, like an 18th order method here, where you see how extremely fast it converges down to numerical precision. So that's numerical precision. Everything else would just be numerical noise of that. But that's just to show you how powerful this method is if you need a higher order method. But we will use this higher order for something else later on. So after we know how to use these spectrally third correction methods and how they work, let's just think about the multi-level extension of that, which is able to overcome one particular problem if you think about time step restrictions. Namely that if you have a very, very costly intensive and time step restricted time integration on the high resolution, we might be able to just do that on a lower resolution by just restricting the solution to a lower resolution, which means that we take this high resolution representation and we apply a restriction on that. It's similar to multi-grid schemes. Then we go down to the lower resolution here, and we can perform some time integration on that lower resolution. Of course, we do some errors in that, not only truncations of linear modes, but also missing or lack of nonlinear interactions. But then we live with it, and we go up to the higher resolution grid again and continue running our simulations on the high resolution. Now the interesting thing is how that works together with the SDC methods, and that's pointed out on that slide. So the first points up here, these guys here, that's depicting the time steps for the spectrally third correction on the fine grid. So that would be one time step, that would be another time step, that would be another time step, that and another time step. And we would do that as a first test run. That's just a first order accurate method which we would apply here, which should run really fast. And then, because it's just first order accurate, and then the solution is taken here at these quadrature points. That works nice if you use these Gauss-Lobato quadrature points. Then we use a restriction down to the coarser resolution. And if you are on the coarser resolution, we can apply more sweeps on that, or more iterations with the SDC iterations, in order to increase the accuracy regarding order on that lower resolution. And now we have a higher order approximation on that lower resolution, and then we can apply that again in order to correct our solutions up here. And of course, for that guy here and for that one here, we need an interpolation scheme in order to correct the solution. Regarding results, let's have a look at these slides, where we can observe that Runge-Kutta 2, explicit Runge-Kutta 2 scheme, which matches the second order SDC scheme, which is exactly what we wanted to see, of course. And we also see a nicely matching behavior with the same SDC scheme. So that's an SDC scheme. The black one here is an SDC scheme, and the yellow one here is the multi. The yellow one is the SDC scheme, not the multi-level version. And we also see that if we use the same order, we also get the same results here, which is exactly what we wanted to see. So we get results which are a little bit better, slightly better at least, for these guys here. But that's just about the time step size. So where we have a larger time step size if you go to the X direction, and that's the error norm, where we also want to have a lower error, of course, and we see some improved results in that range here. But now the really interesting question is, how does that behave in terms of wall clock time? And that's shown here on the left plot here, where less, going to the left side means less wall clock time, and going down here means that we have less errors. And if we just take a moderate amount of viscosity, and we need that viscosity for stability reasons, we see that these multi-level schemes are working slightly better than the SDC schemes. And we observe the same here, where we have slightly better performance using multi-level SDC methods compared to the SDC methods. If we just use a moderate coarsening, so these are exactly the same results as on the previous slide, we see that while we are just slightly better, but now we could also try to use a more aggressive coarsening. So in this case, we only used 4/5 coarsening, and this is now where we use half of the modes in our solution. But then it also turns out that if we use a stronger coarsening, the lack of, so I assume that it's the lack of the nonlinear interactions, that this requires us to add more viscosity to it to stabilize the solution. But then if we do that, we can also observe that using these ML-SDC schemes get an even better wall clock time versus the error, and also for that one here. So that's the ML-SDC scheme versus this SDC scheme, and we see that we get either a reduced wall clock time or we get a reduced error by using the ML-SDC scheme. Well, so far so good about the ML-SDC results. If we are allowed to add some viscosity, let's emphasize that. But now we should think about going to a parallel in time method. So all these steps have been done by us just to get to the shallow water simulations with a parallel in time method. And the way how the parallel in time method is brought into that FAST algorithm is based on the parallel algorithm. And so the underlying idea of that parallel algorithm is that you take your time integration interval and you chop it into coarser time step sizes of time step delta t. And then you take two different time integration methods, namely the fine time integration method, and the fine integration method is denoted here with this curly f. And you also need a coarse time integrator, which is given by that curly c here. And there's one requirement regarding Volt-log time, namely that the coarse time integrator is much faster than the fine time integrator. And there are a lot of other requirements on that coarse time integrator, such as that you require to have a fast convergence with parallel, which is also shown on the next slides. In the ML-SDC context, the fine time integrator would be similar to our high resolution, higher order time stepping scheme, and the coarse time integrator would be related to our lower order time integration and a coarser resolution. But let me first show you some example for that parallel algorithm itself. So as I said, we chop that time domain into pieces, as it's shown here. And the underlying idea is that you can then parallelize in time, so that first rank here would run the computations for that time slice here, the second rank here would run the computations for that time slice here, and so on and so forth. And as a first step, you use a coarse propagator to compute that approximated first guess here. And that runs really fast, so as soon as that one is finished quite fast, it forwards the solution to the next rank, and then the next rank can already run computations for that one. And after that, the first rank here can do some fine time stepping scheme. The fine time stepping scheme in that case would result into that solution here. That's an approximated solution. But in parallel, when the first one is doing these steps here, the second one can already continue running that coarse time stepper and then also running some fine time stepping scheme here based on that initial guess here. And the same happens with the next rank here, where you take that coarse time step as a good approximation for the fine time stepping here, and the same one happens here, and so on and so forth. And then you use an iterative scheme for that, where you hope that while you step by step, if you propagate the solution here, so you get the exact solution here, since that's now converged, there's nothing better than, that's what we assume at least, than the highly accurate time integration method. Then you can take that as a new guess here for the fine time stepper, and you get up to that solution here. Then you can compute a correction based on the coarse coarse solutions here, so on that one here and that one. And you apply that correction to this one here. And then you end up with a new approximated solution here, which you provide to the next rank as a new first guess. So it's a little bit complicated, but if you just follow that iterative scheme, you see how step by step in each of these iterations the overall solution is improving. So that's after the third iteration, fourth iteration, and so we already end up here. That's after the fifth iteration where we end up here, and then you see how the solution is quite accurate already. I'm skipping a lot of details on how the parallel scheme already works, and in particular with the FAST algorithm, but let me just emphasize the three underlying ideas of that FAST algorithm. So first of all, we have this SDC iterative scheme within each part, which and the main motivation of that is that we get a higher order scheme, and higher order is necessary to make parallel, or that's one of the ways how to make parallel converge fast. We have multi-level in space, which allows us to save compute time simply by taking larger time step sizes and to have less workload. And we have a parallelization across the time steps themselves, which allows us to exploit increased parallelism also in the time dimension. So let me show you some results of that algorithm, where we can observe again that by having a look at the full spectrum, that's again wall clock time versus the error results, and less wall clock time means better results, less error means better results, of course. And these are the SDC results, computed with an SDC method, and all these results here have then been computed with the FAST method using the same order as the red one here. So that one here uses the same order as these FAST methods, and we can observe that in particular here we get a significantly reduced wall clock time, and also for that guy here, just by using a moderate viscosity in this case. And the same is the case also for the other norms. If we truncate at a different spectrum here and study the results, we get the same Pareto front given by the FAST method. Okay, so to summarize, with the ML-SDC method, we partially performed better. It's not perfect, but it's quite good. And we needed a viscosity filter for that in order to stabilize the entire scheme. So there are instabilities, which is, I think, one of the future research areas also to investigate where these instabilities exactly originate from, whether it's the nonlinearities or some other strange effects. Regarding FAST, that introduced then the parallelization, and the FAST method itself is finally really Pareto optimal for all these different time step sizes. There is a lot of future work going on where FAST is explored with exponential time integration methods as well. We also thought about getting that running with Lagrangian methods, and as part of that, and as part of the previous presentation, we hope to be able to combine everything together like this exponential semi-Lagrangian and parallel in time spectrally third correction multi-level scheme, which would be then hopefully our final product if everything turns out to work fine. So thanks again for your attention. I hope you enjoyed it, and I'm happy for any questions.